Welcome back to the Lowdown on Physics. This is Screencast 9.1, an introduction to uniform circular motion, part of the Unit 3 VCE Physics topic, motion in 1 and 2 dimensions. The term uniform circular motion is used to describe an object that is moving around a circle of fixed length. It will move around the object at constant speed, and that's where the uniform part comes in. However, what we need to note is, so we've got constant radius, is that because velocity is a vector quantity, it will be continually changing its direction. So speed will remain the same, but the direction of the velocity is perpendicular to the motion. You know, if that was on a string and we were to cut it, it would continue to move straight. It's that string or that force that's pulling on it that allows it to move in a circle. The period of the motion is given the symbol t, and that is the time for one complete cycle. Velocity would be distance divided by time, so we've got 2 pi r gives us the circumference of a circle, and t being the period of that orbit. So velocity, distance over time, or 2 pi r over t. So let's have a look at an example. We have an athlete with a hammer doing the hammer throw. 7 kilo, it has a radius of 1.5 meters, and it completes 3 revolutions per second. So we want to know the velocity or the speed that it's moving around. V equals 2 pi r on t. So we've got 2 times pi times the 1.5, the radius. Then we're dividing it by 1 on 3. That's because it's 3 revolutions per second, so it takes 1/3 of a second to complete 1 revolution. And we get 28.27 meters per second as the speed of the hammer around the athlete. So if we revisit Newton's first law said that if there is a zero net force acting on it, the object remains at rest, or it will keep moving in a straight line at constant speed. Now the object is at constant speed, but to keep moving in a circle it must be experiencing an acceleration, and there must be a resultant force. So it's a non-zero net force because of the continual change in direction. So let's analyse what's happening with the velocity at 2 points in time. So initially we've got velocity, which is at a tangent to the circular path, or at 90 degrees to the radius, and a final velocity some point in time later. Again, final velocity tangential to the circumference and perpendicular to the radius. So if we have a look at change in velocity, final velocity minus initial velocity, then we get final velocity minus the initial velocity, which is adding the opposite direction of the initial velocity, or negative v, I. We get a change in velocity that is in that direction. Having a look at that direction, it's pointing towards the center. So the change in velocity will be in the same direction as the acceleration, and therefore the same direction as the force. So let's have a look then at where the acceleration would be. So we've got acceleration, change in velocity over time. So the direction of the acceleration is always towards the center. Wherever it is in that rotation, acceleration is always towards the center. There is nearly always a question in your exam that asks for the direction of acceleration at a given point, and sometimes mixed up or both the acceleration and the direction of the velocity. So velocity is always at the tangent in the direction it's moving. Acceleration is always towards the center. Force, therefore, will always be towards the center. So just remember that one. There's a bonus gift mark that they nearly always ask. So let's have a look at how we calculate acceleration. I'm going to reiterate, direction towards the center. You'll be sick of me saying it by the end of this topic, but hopefully it will have sunk in. Now, It's not quite as straightforward because of the rules of circular motion. So basically I'm just going to give you the two rules. We've got A equals V squared on R, or 4 pi squared R on T squared. Now this is a rearrangement of V squared, where V equals 2 pi R on T. So rearranging that, substituting in V equals 2 pi R on T, we can produce that. I will redo that, or I'll do that in class for you so you can see the rearrangement, but I'd encourage you to have a go and see if you could substitute that in and come up with that before class. So if we have a look at this example, we have a 0.5 kilogram mass on a radius of 0.8 meters. Period of motion is 1.5 seconds. That's 1.5 seconds per cycle or per revolution. So velocity is 2 pi r on t. We get 2 times pi times 0.8 divided by 1.5, straight substitution in. We get 3.351 meters per second. Second question asks us, what's the acceleration of the mass? Well, A equals 4 pi squared r on t squared. Using that, we don't use a rounded value. Alternatively, we could do v squared over r. Try it both ways on your calculator. See if you come up with the same answer. You get 14.036 meters per second squared, direction towards the center. And finally, the tension in the string. If we're talking about tension in the string, well, that's the force that's actually pulling it towards the center. So F equals ma. We've just calculated A, multiply that by our mass, we get 7.018 newtons. So things to note about force. You know, where there's smoke, there's a fire. Where there's acceleration, there's going to be a force. So we've got unbalanced force causing this acceleration and keeps it moving in the circle. Now F equals ma. A is v squared over r, so we've got mv squared on r, or m 4 pi squared r over t squared. Now, things to note is the centripetal force is constant in magnitude. It's always directed towards the center of the circle, and it is provided by, must be provided by an external source. Okay, so in the case that we just had, either a string, the tension pulling it in, or here we've got reaction force with the road. Friction is what causes that centripetal force. Friction by the tyres again, centripetal force. Here we've got tension, tension again. We've got normal reaction force in the case of this roller coaster. In this case, we've got gravity. And of course, to keep the moon orbiting around us, we have centripetal force by gravity. Check out that animation. Alright, that's it. See you in class.